Everyone, good morning. Let's solve the questions from Quiz-2. And this time again, I have taken 5 questions, and you can see there. These are the 5 questions, and we'll solve it and discuss it one by one. So let's see the first question, and this is asking like which of the following is not a ferrite stabilizer. So basically, we know that a ferrite stabilizer stabilizes the you know ferrite phase in a steel, and these are basically having BCC crystal structure like chromium, molybdenum, tungsten, vanadium. These all are having BCC crystal structure, as well as one more is that silicon, which is having diamond cubic crystal structure. So these are the elements like chromium, molybdenum, tungsten, vanadium, and silicon stabilizes the ferrite. So these are known as ferrite stabilizer. So if you see carefully, chromium is there, silicon is also there, copper is not present there. Tungsten is also there, having the highest melting point, and the metal having very high metallic bond strength in that. So that the answer will be simply copper. So this is going to be our correct answer for the first one. Copper is basically an austenite stabilizer because copper is having FCC crystal structure, and that stabilizes the FCC phase of austenite. Second, select incorrect statement about the white cast iron. Okay. So the first is fracture surface looks white, and that is absolutely true. That in the white cast iron, the fracture surface looks white. Has high wear resistance. Yes, white cast iron has very high strength, and we can say due to high carbon, it has very high wear resistance also because of very high hardness. And hardness is high means hardness increases means wear resistance increases. If hardness is high means wear resistance will also be high. Third is absorbs high energy prior to fracture, and that is definitely going to be incorrect, because if the hardness is high, then the material will be brittle in nature, and the brittle material absorbs a very low amount of energy prior to deformation or fracture. So this is absolutely wrong. Used in balls for grinding mills, of course. This is used as a ball for the grinding mills, and that is absolutely true because these balls will have very high hardness, and it having a high wear resistance. That is why it can be used in the grinding mills. So the incorrect statement is the third one. So this is going to be the incorrect statement, that it absorbs high energy prior to fracture. Moving to the question number 3. Again, let's see. We have to select the correct statements. Okay, so it is of MCQ type. We can have more than one correct answer. First is for Fe3C formation, that is cementite formation, 100% segregation of carbon is required. And this is completely wrong, because Fe3C, that is the cementite phase, has only 6.67% carbon. So this does not require 100% segregation. So this is wrong. Second is graphite has lower free energy than cementite. If we see that energy diagram, Fe3C is metastable. Fe3C is metastable, and graphite is stable. Graphite is the most thermodynamically stable electron of carbon as also. It is more stable than diamond also. So if we compare with the cementite and graphite, we can say if the graphite is more stable because it is a stable phase, and the Fe3C has metastable because it is between unstable and stable, so it will have higher energy. And here it is saying that graphite has lower free energy than cementite or Fe3C. So yes, it has a lower in energy, higher in stability. So this is going to be the correct answer. Next, slow cooling of casting favors Fe3C formation. So let's see. They are asking slow cooling of casting favors Fe3C formation. And I think this is also wrong, because if the cooling rate will be slow, like in sand casting, if you uh, just cool it in air, like air cooling will be done, so it will have very high time, or more time will be given to that the phases, like for the graphite phases, so carbon can segregate very easily, and 100% segregation can occur if you are providing more time. So in slow cooling, you are providing a high amount of time, you can say, and that's the region the segregation of the carbon will be more, and in that case cementite formation will not take place, because if the carbon is getting more time, it can segregate 100%, and here graphite can forms, or graphitization can take place, and that is wrong. In fast cooling, basically we get cementite, that is Fe3 formation, Fe3C formation can take place. In slow cooling, we will have high segregation and it will form graphite. Or we can say chill casting. Chill casting means you are rapidly cooling it by adding water. So in this case, we will have cementite formation. Now, graphitization is enhanced by silicon. So this is a fact, and you have to remember that is also correct statement, that a silicon has an unusual property, and it shifts the temperature gap between graphite line and the cementite line from around 6 degrees centigrade to 35 degrees centigrade. Okay, so basically this silicon element shifts the temperature gap between the graphite and cementite line from 6 degrees centigrade to 35 degrees centigrade. Okay, with addition of very small amount of silicon, only by 2% silicon, and we can say that yes, silicon is very effective in graphitization. So this is also true. So the correct statements are 2 and 4. Next, we have to match the following. So it's the match the following type questions, and we see A is silicon doped with boron, aluminum, or gallium. So these all elements are from the same group, boron family. All are having 3 valence electron, and this boron, aluminum, and gallium having the 3 valence electron. When doped in silicon, silicon having the 4 valence electron, then there will be deficiency of electron. Okay, so a hole will be created. So what we can say, the hole, that will be the electron acceptor, that it will match with the P. Then the conduction will be primary by holes, so it will match with the T also. And the conduction primary by holes is taking place in p-type semiconductor. That particular semiconductor is of p-type, so it will match with R also. Similarly, silicon doped with Phosphorus, arsenic, or antimony, these are from the nitrogen family where each having 5 valence electron and the silicon has only 4. So during doping, one extra electron will be left. So it is excess in electron, so it will be electron donor. It will be electron donor, so it will match with Q. And in which conduction will be primarily by electrons, so it will match with U also, and it results in the formation of N-type semiconductor. So you can have this match. So A is matching with P, R, and T. B is matching with Q, S, and U. Let's see the next question. Again, we have to match the following. We have given the cooling rate, the structure, and the industrial process. If the cooling rate is 100 degrees centigrade per second, it's a low cooling rate. Okay, so in this case, also not very low because it is 100 degrees centigrade per second. So if the iron is at suppose 700 degrees centigrade, so within 1 second you are bringing it to 600, next second you are bringing it to 500, then 400, then 200, so again then 300, then 200. So it's not a very low cooling, it's a high cooling also, but not very high. So in this case, what will happen? Will I get metastable crystal structure? Sure, no. Metastable crystal structure we get if the cooling rate is very high, like martensite formation, that is the metastable phase, very high cooling rate. Fine grain size, yes, we can get very fine grain size, again no. So this will match with Q. In this type of cooling rate, we will get fine grain size. After that, this special type of process is related with chill casting. So this is chill casting, and this chill casting has this type of cooling rate, that is 10⁻² degree centigrade per second. Next is if the cooling rate is between 10⁻³ to 10⁻⁴ degree centigrade per second, then in this case we are going to get very fine grain size, and this special type is called as RSP, or we can say rapid solidification process. So it will match with this. And see the last one. If the cooling rate is extremely high, or we can say 10⁻⁷, then in this case 10⁻⁷ is too high, then glass formation can take place. Bulk metallic glass can also be formed in that case if the liquid is directly cooled with this much speed. So this forms basically metastable crystal structure, so it will match with P. And this special process is called splat quenching. That's the splattering or splat quenching. So these are the final match. So again, A, Q, and Y are matching. Then B, R, and W is matching, and the C is matching with P, and here it is matching with X. So that's the end of this lecture. Thank you very much.